I would like to recall first L'Hôpital's rule. Yes, we say L'Hôpital, not Le Hospital. Suppose that f and g are differentiable functions at x equals c, and that limit of f and g when x approaches c is 0, or the limit of f and g when x approaches c is any combination of plus minus infinity. Then limit of fx over gx when x approaches c equals to the limit of the derivative of x over the derivative of g when x approaches c. We also have written the shortcut of L'Hôpital rule. The indeterminate form of a function to the power of another function. F to the power of g I'm going to write it a little differently. I'm going to write it as e to the power of ln of f to the power of g, using the rule that a also equals to e to the power of ln of a. Now I'm going to simplify this using rules of logarithm. I know that ln of x to the power of a is a times ln of x, and I get e to the power of g times ln of f. Now let's also add the limit. First I'm getting this. Now I'm getting this. And now I would like to recall some theorem about limits that we did long time ago that says that if a function is continuous, you can switch the limit and the function, which means the limit of e to some function is also e to the limit of this function. So here I'm switching the place of the limit of x approaches c to be in the exponent of the e. And I get that this is e to the power of this limit. And if this limit is L, we get e to the L. We're going to do a few examples. Example: the limit of x to the power of 1 over x when x approaches infinity. I would like just to recall that if you need to differentiate the function x to the power of 1 over x, you have to use logarithmic differentiation. So now when we have to take the limit, it's exactly the same idea. We cannot take the limit of such function. We have to change the way it is written. And the best way is to use that everything is also e to the power of ln of that. So first of all, before we even do that, we want to see what is this form exactly. 1 over x is 0 when x approaches infinity, and x is infinity when x approaches infinity. So this is this form, which is pretty nasty. You don't want just to apply e to the ln and do all this work to figure out a limit which is trivial. For example, if this was infinity to the power of infinity, then the answer is just infinity. So you want also to see that this is indeed indeterminate form. And now I see that it is. First, I'm rewriting x to the power of 1 over x as e to the power of ln of x to the power of 1 over x. Now I'm simplifying this using rule of logarithm, and I get the limit of e to the power of 1 over x times ln of x when x approaches infinity. But I can write this much better like this, okay? Now I'm switching the e and the limit. And I get that. I don't know if you remember, But this one is pretty easy. ln of x at infinity is infinity, and x is infinity at infinity. So this is just infinity over infinity, and I can go ahead and use L'Hopital rule. And when I use L'Hopital's rule, I get that this is exactly the limit of 1 over x over 1 when x approaches infinity, and I get 0. It means that the limit of x to the power of 1 over x when x approaches infinity is e to the power of 0, and e to the power of 0 is 1. Example: limit of 1 plus 1 over x to the power of x when x approaches infinity. This form is 1 to the power of infinity, and the reason is because 1 over x in infinity is almost 0, and we get 1 plus 0 to the power of infinity. But I have a surprise for you. This limit is not 1, because you don't have 1 to the power of x or 1 to the power of infinity really, you have 1 plus 1 over x. So even though the form here is 1 to infinity, it's not really 1 to the power of infinity, but it is 1 plus 1 over x to the power of x when x approaches infinity. Okay, so let's do that. And again, you want to notice that this is a function of x to the power function of x, so I have to do that. Now I'm going to use rule of logarithm to simplify ln of 1 plus 1 over x to the power of x, and I get this. I also switched the e in the limits because I know that it is possible already. And now I have to evaluate this limit. This is not an easy limit. Look at the form of this limit. When x approaches infinity, x is infinity, but ln of 1 plus 1 over x, when x approaches infinity, 1 over x is almost 0, and ln of 1 plus 1 over x is almost ln of 1, and ln of 1 is 0. This is the indeterminate form infinity times 0. I hope you remember the trick. Instead of multiplication by x that we have here, we have to divide by the reciprocal of x, which is 1 over x. And we get that. ln of 1 plus 1 over x when x approaches infinity is a ln of 1, which is 0. And 1 over x is 1 over infinity, which is 0. Now I have 0 over 0, and I can go ahead and apply L'Hopital's rule. I would like to remind you that the derivative of ln of a function is the derivative of the function over the function. It's going to be handy here. And I get that. So it is the derivative of 1 over x over 1 plus 1 over x over the derivative of 1 over x. I simplify that. Now I can cancel that. You see, I even was lazy and I really didn't calculate the derivative of 1 over x because it cancelled out. And I get this. The limit when x approaches infinity of 1 plus 1 over x is 1 because 1 over x approaches 0 when x approaching infinity. And I get that. Now don't forget that this is only the limit, which is the exponent of the e. The limit of what we are looking for, which means the limit of 1 plus 1 over x to the power of x when x approaches infinity, is e to the power of 1, which is e. The last the limit is actually a theorem, and it's also one of the definitions of the number e. So here is a theorem. You would like probably to memorize that. The limit of 1 plus 1 over x to the power of x when x approaches infinity equals to e. The matching theorem is, which is exactly equivalent to this, is that the limit of 1 plus x to the power of 1 over x when x approaches 0 from the right equals e. I would like to note that in this theorem there is part that can be manipulated and there is a part that cannot be manipulated. Because I have something in parentheses to the power of x, the stuff that is in the parentheses, it's locked in. On the other hand, we can use rule of exponents to manipulate this one. It's the exponent, easily manipulated. Now we're going to evaluate using a limit using this theorem, and you will see how you can really manipulate the exponent. We are going now to evaluate the limit of 1 plus 1 over 3x to the power of x approaches infinity, using the theorem. This will save a huge amount of time. We notice that the 3x is in the part that it's locked in. There is no way to manipulate the 1 plus 1 over 3x as it is written right now. But also, I noticed that when x approaches infinity, also 3x approaches infinity. So the fact that I have 3x instead of x, it's not a huge deal. But look at the theorem. If I'm going to change x to 3x, then I still need that the exponent is going to be exactly like this thing that comes in the 1 over, which means I want my exponent to include 3x. Let's do the algebra. It's pretty simple algebra. I want to include 3x, but I have only x. So it is 3x times 1 over 3. I didn't change anything. But now I can use rule of limits, and rule of limits allows me to just gather this and then apply the 1 over 3. Now I'm observing that in the brackets I have exactly the theorem. Again, nobody cares if I have 3x instead of x, because when x approaches to infinity, 3x also approaches infinity. This is e. And I get e to the power of 1 over 3, which is cubic root of e.